Hi, this is Miss Litton, and this is my wonderful Period 1 AP biologist, Isabel's. Say good morning. All right, happy Tuesday. Is that what it is? All right, so we are picking up in our notes. We're talking about Mendelian patterns of inheritance, and we're going to talk about dihybrid crosses right now. All right, so do you remember what independent assortment is about? Yes or no?
Oh, okay. I'm guessing yes. Get it wrong. Isn't it just
You're having a quiz on this at the end of class, so yes, yay, good job. Riz first. All right.
Is that a money?
No. So independent assortment means during what stage? What stage are you looking at right here? Oh shoot, it's labeled. What is it? Dang it. Metaphase 1. That each homologous pair can line up independently of the other. Now, so far, we have only discussed looking at one trait, traveling all by itself. Tall, short, round, wrinkled, lizard eyes, black, lizard eyes, yellow, right? Now we're going to be looking at more than one trait traveling together. And when we do that, it's going to depend very much if they're on the same chromosome or they're on a different chromosome. If they're on the same chromosome, these two traits right here are more than likely going to travel together because they're linked genes. They're on the same chromosome. Unless what happens? Crossing over. When's crossing over going to occur? Right. If they are not linked and they're on two different chromosomes, these two right here may travel together. But if this chromosome pair lines up flipped, they may not travel together. Okay, so let's take a look at that. Okay, so here we have our dad chromosomes are in blue, and our mom chromosomes here are in pink. And if they line up this way, looking at these different traits, okay, here is this individual's genotype. It has big B and little b on one homologous pair, and it has big E and little e on another homologous pair. You okay with that? All right. So if we do, I need you focused, okay? If it lines up in this manner, what are the different kinds of gametes we could get from this individual? So right here, this would give you a what? A little b and a big E. That would be one kind of gamete. What would be the other gamete? Big B and what? Little e. These would be the two types of gametes if they lined up this way. Okay, check with your bio buddy right now that they get just this first part, why I pick these as gametes. And let me ask you a question. What law says I will only get one kind of B, either the big B or the little b? What law says that? Law of segregation. Okay? Okay, look right here at me for a minute. You're looking at your notes or around, and you know that I love you, but you got to dial it in, this big ticket item right here. Okay, dialing in. Okay, so law of independent assortment says they can line up any which way they want. Law of dominance says big B is dominant over little b. Law of segregation says when I'm making my gametes, I either get the mother's big B or the dad's what? Little b, because the homologous pairs are going to do what? They're going to separate. So I could get little b with big E, and that's what we have right here, and big B with little e. But what if they lined up instead like this? If they lined up like that, what are my possibilities? I could get what? Little b with little e, and big B with big E. So I have 4 potential gametes. When I'm just looking at just 2 traits, I have 4 potential gametes that I can end up getting. Okay? That, my friends, is the law of independent assortment. Now, one way you could come up with these 4 gametes, do you remember FOIL? First, outside, what? Inside and last. So FOIL would say you could get a big B with a big E. There it is. Inside would say what? First, outside would say you could get a big B with a little e. Inside would say little b, big E. And last would be little b, little e. So riddle me this. If I had this, what are all the possible gametes I could get from this individual? Write it down on your paper. Write it down on your paper. Don't say it out loud. Show me with your fingers how many gametes did you come up with? Did you say 4? Okay, and this is the way you would write them. Big R, big Q, big R what? Little q, little r, big Q, and what? Good. Okay, how about this? How many different gametes could I get from this? Write it down. Show me with your hands, how many different gametes could I get? 2. I could get big A with little b, or little a with what? Little b. Okay, every single time I'm going to get a little b. Why would I never see a gamete like that? Yes, say that again, Max. Nice. Yes, law of segregation says you're only going to get 1 b. That's what the law of segregation says. You're only going to get 1 B. Okay, good job. So now let's take a look at this parental cross. These are P's, and the trait is round or wrinkled, okay, and yellow or green. Now, just based on how I put it up there, what traits are dominant? Round and yellow. Okay. Now, how many different gametes could I get from this individual right here? How many different gametes could I get from this individual right here? Do that cross, right? Don't do the cross, just identify the gametes. Write the parents, write the potential gametes. Okay, now tell me, how many potential gametes do I have for this parent right here? 1. What is it? Okay, that's not helpful. Big R and big Y. Let's make this sperm. Okay. How many potential gametes do I have here? 1. What is it? Little r and little y. Okay. So if this fertilization takes place, I would have a big R, big Y, little y. Do you agree with that? Okay. Now, this is my parental generation. This is my F1. I want to cross 2 of these. How many different gametes? So I'm going to cross big R, big Y, little y with another one. How many different gametes could each of them make? Tell me right now. Work them out. How many different gametes could each of these make? Work it out. Work it out. Work it out.
Big R, small R, big Y. The thing on the left, is that like another cell? Or
this is sperm. This is egg. Fertilization takes place. This is a zygote right here. So now I'm crossing these 2 zygotes. Okay. So how many different gametes can I get from this individual? 4. What are they? Big R. Do you agree with that? Yes? How big does our Punnett square have to be if I can get these same ones over here? How big does our Punnett square have to be? 16 squares. That's a honka pajamas Punnett square. Do you agree with that? If I did this, okay, because I would have big R, big Y, big R, little r, big Y, little r, little y, and same thing here. Do you agree with me? Now, I'm going to make sure you understand this first, and then I'm going to show you a shortcut. Okay? So now, what I want you to see here is if this sperm right here fertilizes this egg, then it would be big R, big R, big Y, big Y. Do you agree with that? How would that look like phenotypically? Round and yellow. Yes? Okay, now you're going to have to think on your feet and tell me what to pull. Okay? So, if this sperm fertilizes this one, what's it going to be? Round and yellow. Can I show you one trick? Every single time this is going to give a big R, and every single time this one's going to give a big Y. So do we even care what these are? No. What are they always going to be? Round and yellow. Make sure your brain understands that, and your bio buddy's brain. Can we find another column or row we can do that to? What one? This one?
Yeah.
Okay, because it doesn't matter what these are, this is always going to give what? Round and yellow. Are we okay? Now, think about this one. What's this one going to be? Round and green. What's this one going to be? Round and yellow. What's this one going to be? Round and green. Okay. Now, what's this one going to be? Round and good. What's this one going to be? That's good. What's this one going to be? Perfect. What's this one going to be? Round and green. Okay. What's this one going to be? Wrinkled and yellow. And what's this one going to be? Wrinkled and green. Now, based on phenotypes, how many different phenotypes do we have? This is called a dihybrid cross. Here's one hybrid, here's the second hybrid. So it's a dihybrid cross. How many different phenotypes do we have? Discuss with BioBuddy. Quickly. Okay, so give me the ratios here. What is the most dominant one you have? Okay, you guys, do it in the same order I gave it to you. Round and yellow. Okay, so you have round and yellow. How many round and yellows do you have?
9.
Count them. How many? 9. Okay. Give me the next one.
Round and green.
Round and green. How many do you have?
3.
3. Give me the next one.
Wrinkled and
Give-
yellow.
Okay, wrinkled and yellow. And how many do you have? 3. And give me the next one. Wrinkled and what? Green. How many do you have? 1. Okay, so you had 9 out of 16, 3 out of 16, 3 out of 16, and 1 out of 16. Do you agree with that? Okay. That was a dihybrid cross. What would happen if we did a trihybrid cross? How many would we need then? Yeah, 64. It's getting bigger and bigger, right? So let's do a shortcut, okay, with our product law. So we knew this is what we were crossing. Do you agree with that? Now, what if I wanted to ask you how many would turn out round and yellow? That's, if I do this cross, how many turned out round and yellow? That's what I'm wanting to know. Here's how you solve it. Cross your R's all by themselves. And you guys, right now, we're writing out the punnets, but pretty soon you will see the punnets in your own mind. You'll smell the punnet. It will be there. Okay? So cross round all by itself. And then cross yellow all by itself. It's going to look remarkably similar. Do you agree with that?
Yes.
Okay, thank you. So how many turned out round over here? 3 out of what?
4.
How many turned out yellow over here? Out of how many? Product law. 3 times 3 is? 4 times 4 is? 9 out of 16 turned out round and yellow. So you can solve any problem now because you do individual punnets and multiply the probabilities together if they happened at the same time. Product rule, right? Like when we said a penny, half the time it would turn up heads, right? Half the time it would turn up, the second penny would turn up heads. So what were the odds of 2 pennies turning up heads? A half times a half was a 4. Same thing here. You're just applying your product rule to this dihybrid cross. If I asked you, how many would you expect to turn up wrinkled and green, right? So do wrinkled and green now. This would be wrinkled, right? How many turn up wrinkled and green? 1 out of 4. And green would be what? 1 out of 4. 1 times 1 is 1. 4 times 4 is 16. Easy peasy, lemon squeezy. Now, we only did phenotypes here, right? But we could have done genotypes. I could ask you, how many of them will turn up like this? Could you tell me? Of the offspring, how many would turn up big R, big R, big Y, little y? Work it out. Not out loud, not whispering it to your neighbor. Work it out yourself. Write it down so you know you can do it. Yeah. So how many turn out big R, big R? That would be what? 1, what? Right here, big R is 1 out of 4. How many turn out big Y, little y? 2 out of 4. Simplify it. 1 over, oh, sorry. 1 over 2. 1 times 1 is 1. 2 times 4 is 8. 1/8 of the time you would get this genotype. Yes?
So this solves for the genotype and phenotype, you can do it.
You can ask whatever you want out of it.
But if it was asked, like, how many times will you get capital R and lowercase y?
Kate, stop and listen to yourself for a minute. If you're saying capital R, little r, those are all genotypes. If I say words like round and yellow, that's phenotypes. When you look at this right here, you know it's round and yellow.
Yeah.
But I was asking for this particular genotype. Because there are multiple ways to be round and multiple ways to get yellow, right? I was asking big R, big Y, little y.
It's more specific to that.
It's just something different. So here you go, my friends. Solve it. Okay, try to do it by your onesie and then put it in. Fraction answer, use your clicker. Don't give it away now. Just keep it to yourself. Can you see the punnet, or are you having to draw them all? Smell the punnet. They all smell the same to me.
Let's
Ooh, I like it. Alliteration.
Thanks, I'm accounting for it.
Oh my gosh.
I live with alliteration.
I just did math like yesterday.
Pause this because it's taking too long. Okay, those of you still working it out, I want to work with you, okay? A little bit. So big A, little a, big A, little a. If I'm imagining that Punnett in my head, how many times will the offspring turn out big A, little a?
2.
How much? 1/2. Because a fourth of the time they'd be big A, and a fourth of the time they'd be what? Little a, right? Did you see that Punnett in your head? Big A, little a, big A, little a, big A, big A, big A, little a, big A, little a, little a, little a. 1/4 would turn out that. Okay? Then if I do my next one, the B's. Now every single time, when you see something like this, every single time they're going to give a what? A big B. Do you agree with that? So just shortcutting it out, how often will this one give a little b? How often? Okay, so let's do the b's. Okay, so I've got big B, little b, crossed with big B, big B. Big B, big B, big B, big B, big B, little b, big B, little b. So how often is it going to turn out big B, little b? 1/2. You got it? Come back. Yes. Yes. Then I need to look at R-ness. Okay? Do you see what I'm saying? Every single time they're going to give a what? Little r, right? How often will this one give a big R? 1/2. So it's going to be 1/2. You can do the Punnett to see it. Big R, little r. Little r, little r. You with me? Okay, so now just do the math. 1 times 1 times 1 is 1. 2 times 2 is 4. Times 2 is 8. Ah, only 66% of you got that. Look at that on top. Okay, check with your bio buddy. Did you get it right? Or did you struggle a little bit? Do you understand that? Do you need me? Here. Okay, no problem. Here, do this one. Start to see the Punnett in your head. Okay. Okay. Okay, perfect. So you see the I won't do it. Okay. Do you want me to edit it? Do you want me to see if I can edit it?
Yeah, I
Okay.
can see if you can.
Okay, I'll pull it on my phone.
Okay.
Oh wait, no. I just like
up and smell the punnet.
That's a good like chocolate stick.
It is. What's that movie? I like the smell of punnets in the morning.
Jurassic Park.
No, it's napalm. What's that war movie?
There's a lot.
Oh my gosh, I can't believe I can't remember this.
I always get a rose.
Google it.
I have a 0%.
What?
Google it. The smell of. I can't believe I can't remember. Yeah, napalm in the morning. I can't believe I can't remember
It's
this movie. Sheen was in
Apocalypse
it.
Now.
Apocalypse Now. Thank you very much. Don't watch it. It's a horror movie. Scary.
That's a good movie. Never seen it. I have seen parts of it. I watched the trailers. Any movie I read.
Okay, so riddle me this while we're waiting for a few people to finish up. How often are we going to get a big A from this cross? 1/4. Right? Okay. How often are we going to get a big B, little b? Half. How often are we going to get a little r, little r? Because it's only, 1/2. So 1 times 1 times 1 is 1, 2 times 4 is 8, times 2 is 16.
I kind of see the
Oh. All right, here you go. Don't say anything out loud. I want you to do this one all by yourself. Don't say a word. Once you put your answer in, though, you can look at me. But don't say anything out loud. Make your partner do it by themselves. Make them do it by themselves. So many punnets, so little time.
Jeremy's loving This is one of those ones that has 20 minutes after.
Max? 5, 4. Oh yeah, do your math. Do it. Whoa. Come on, 2 more punnets. You can do it. You can do it. 2 more punnets. 2 more punnets. 3 more punnets. 4 more punnets. 5 more punnets. The answer is 0. Listen, read your questions. Okay? This was ruled out because at no time you were going to get big R, right? Because they only had little r's to get. So always read through your problems. Okay? All right. So you could get a cross like this. How many different phenotypes do we have?
4.
What do you think the dominant trait is?
Brown, smooth.
Round and brown or round and purple?
Wait, where's purple?
This is Indian corn. It's kind of brownish purple on mine. So you have four different phenotypes. Your eyes are here. Not sure what the struggle is today. Okay. So you have round and purple. You have wrinkled and purple. You have round and yellow, and you have wrinkled and yellow. You should be able to take something like this, you should be able to add up. If you were guessing, if you were going to predict, you should be able to look at this and figure out, what do you think is the dominant trait? And in this case, you're telling me round and brown or round and purple. Okay. Did you already send it to me? Okay. Round and purple. And then if that's the dominant trait, then what is the absolutely recessive trait? Wrinkled and yellow. And then you would count up the numbers, and you would see how many. You want me to view it in my calendar? That's what it said?
Yeah, can you? Look at it. I'm sorry, guys.
And then you should be able to figure out.
It starts today, though. How can I get it to go to where I wanted to start. I'll figure
Okay.
it out.
I can help you at nutrition.
Thank you.
Okay. All right. You should be able to then predict by how many corn kernels you count up what you would predict. In this case, is this a dihybrid cross? You should be able to do, if it's a dihybrid cross, we would expect what? 9 to what? 3 to 3 to 1. Do you see what they're asking you to think about here? And then you should go, now that I have those results, could I do a chi-square, and are these numbers acceptable for how much it is off? Okay? And I want you to be able to do that if we have time at the end. Okay? We could go through and do this and count. You know, in this case I said purple and smooth, purple wrinkled, yellow smooth, yellow wrinkled. Count up the total you count. And if you counted 75, you would expect 9/16 of those 75 to be purple and smooth. Are you with me on that? 3 and 16th, 3 and 16th, 1 and 16th. And then from that, you would go, okay, well, how much were we off from what we observed to what we expected? Do your chi-square test. If you have 4 different phenotypes, how many degrees of freedom do you have? 3. 3 degrees of freedom. And then you would say, does it fall or is it unreasonable? Do I need to consider another hypothesis for how that would turn out? That's what I would expect you to be able to do, okay? And do the expected and the results and then work it out just like this. Okay, so in your notes, if you haven't put this in from the PDF of the notes, take a picture and put this in, because I want you to try and do it, okay, and see if you can do it, and then we can talk about it in the review. So grab the PDF, that picture. Okay, work out your chi-square value. Okay, and then just see if you can do that, because that would be a real application. All right. Now, on your notes, go back in your notes where it says Law of Independent Assortment. And we have, in summary, think of metaphase what? 1. Each pair of factors or alleles segregates, we have that word, right? Assorts independently of the other pairs. All possible combinations of factors can occur in the gametes. Then it says 2, dihybrid cross, and 3, it says examples. Blue, can you take on 2 and 3 right there and review that? All right. Okay, so now let's see if I did that here. Oh yeah, we all that. Okay, so now we're gonna that's kind of backtracked into dihybrid crosses. We should right now be on 11.3 Mendelian patterns of inheritance in human disease. Are you there? Yeah. Okay, so this is a pedigree. All right. Females are what shape in a pedigree, do you think? Circles. And males are square. And if you are affected, then it is colored in. So this is one pattern. Now, knowing what you know about dominant and recessive, if I was looking at a disease right now, and this you were consulting, you were a geneticist, and you were consulting this family, and this is how it played out, would you predict that this is an autosomal dominant disease, an autosomal recessive disease? And what is your evidence? How would you support that claim? Discuss. Okay.
Our computers are both offline.
Is anybody else's computer offline?
Yeah.
What? Okay, go to CNN and then come back. It's some other site other than our school. They always say, go to CNN.
The liberal media.
Liberal media. No, that's MSNBC. And I watch that too.
I love MSNBC.
They're all fake news,
Except for Fox, and then that's no spin there. Okay, come back to me.
Nope.
Now, let me tell you what I'm observing, okay? Let me tell you what I'm observing as your teacher that loves you. I know you had an English test, right? And that was hard. Okay? And I know you have a quiz, okay? But today is your least engaged day that I'm having. I have to keep pulling you back in, and it takes me longer to teach you. And I know you're thinking about your quiz, okay? But we need to think about this right now, okay? So you got to dial it in so you understand it. This is the third time I've asked you to dial it in, okay? So stay focused so that you understand everything. All right, now, if I was going to use the letter A for my genotypes, what genotypes would you give each of these individuals if I was using A-ness as genotypes? What genotypes would each individual have? Okay, what do you say right here?
Big A, little A.
Big A, little a here?
Big A, little A.
And?
Little A, little A.
Yes. Okay, now, could you have two parents who don't have a disease and it pops up in the child? Yes, absolutely. What kind of disease would we classify that as? Recessive disease. Could you have two parents that don't have a disease and the disease pops up in the child and have it be a dominant disease? No, because dominant diseases can't be what? They can't be hidden, right? You can't mask them. Now, there is something that we're going to talk about called penetrance and expressivity. Penetrance is how often is the trait displayed. You know, usually it's displayed. For instance, if you get an XY chromosome, usually you're going to be a what? Boy. Have there ever been people who get XY chromosomes and present as a girl? Yes. Their Y chromosome was hidden, and they grow their whole life thinking that they are a girl, okay? But their Y chromosome was somehow masked. There's also something called expressivity, and that's how you express it. For instance, syndactyly is webbing in your fingers. For some people, when they have syndactyly, there might be just a little bit of webbing between their ring finger and their pinky finger. For others, though, it can be full-on webbing, okay? It can express itself in different ways, expressivity, okay? So those two things come into play, and those would be exceptions to the rule. Do you think if we bring in a disease that's on a sex chromosome, it could vary whether or not offspring get it? Yes, because girls get how many X chromosomes? 2, and boys only get what? 1. So if it's a sex-linked disease, a girl has to get 2 bad X's in order to express that disease, right? But a boy only needs 1. And where does he get his X chromosome from? His mom. Because what made him a boy that he got the Y from his dad? It doesn't even matter if his dad has the disease or not, right? So when we start talking about inheritance patterns, we need to know, is this disease autosomal or is it X-linked? Is it dominant or is it recessive? Yes?
So let's say there's a couple and the dad starts smoking and gets lung cancer, then they have a child. Is the child at risk for cancer? Or is
Okay, so let's think about that. That, when he's smoking and he gets lung cancer, not to be gross, but are his testes smoking?
Well, couldn't it spread though to his whole body?
No. Now think about it, okay? Was his DNA, if his DNA and his testes aren't, the part that's getting damaged are things like his lungs and probably his bladder and potentially his mouth. Because that's the part that is exposed most to the carcinogen. Because you would get rid of those carcinogens and then they'd be in your bladder and then you hold your pee for a while, so it wouldn't be unlikely for you to get bladder cancer as a result of smoking as well, okay? But his testes are not impacted by that, so he's not passing that trait on. Now, how about the tendency for addiction? That he could pass on, right? Yes?
Would colorblindness be affected by the dad's chromosome or the
Okay,
mom's?
so all of these questions that I gave you were probing questions to make you think about what we were going to do, but we're going to talk through them all right now. So I'd like to talk through them. Yes?
So could diseases be passed down with the Y chromosome too?
Yes, those are called holandric traits, but a Y chromosome would be passed on to the boys, right? There's very few genes there are powerful genes on the Y chromosome, but it's small. There's not a lot of traits on there. One of those is having a hairy pinna, You know, like when you see grandpas and dads with hair like shooting out of their ears right here? That's on the Y chromosome. You don't see a lot of women are like, I gotta trim my, you know, my ear hair, okay? Those trimmers are all geared towards men, okay? All right, so let's talk about pedigrees now. Now, if you look at this pedigree, this is a pedigree of a family with hypercholesterolemia. So they have too much cholesterol coming out. It can cause swelling and real gnarled hands, etc. Now, this is an autosomal dominant disease. How, looking at this pedigree, could you support, oh, I could see how that's an autosomal dominant disease. Have that discussion right now. Autosomal as opposed to sex-linked. Go ahead, have that discussion with your bubba.
Well, the children, they have it. Because the father has it and their kids have it.
So give me some genotypes. Dad has it. What could his genotype be? He has the disease. Let's use the letter H because it's big H. Do we know what his second one is? Okay, so we'll leave it for right now because we're not sure. What is mom? Little h, little h. Do you agree with that? Okay, how many children did they have? They did not have 8 children.
They had 3.
5.
4, 5. Oh, yeah.
1, 2, 3, 4, 5. Did all of their children get the disease? No, not all their children got the disease. Now you know every single time what was mom giving to all 5 of these children? A little h. That's all she has to give. Do you agree with that? So every one of these kids got a little h from mom. Okay? So this individual right here, number 3 of generation 2, this son doesn't have the disease. Okay? So where did he get his other little h from? From dad. So dad must be what? Yeah, he must be a heterozygote because he had a son who did not get that disease. Are you with me on that? Okay, so this son definitely got the big H, but who did he get the big H from? From the dad, right? His wife that he married is little h because she doesn't have the disease. This boy got both their little h's. This girl got the big H from dad, and you know they got a little h from mom. You could go through here and predict everybody's genotype all the way through. Okay? And here we know their little h, little h, little h, little h, so all of their children did not run any risk of what great-grandpa had. Because it was an autosomal dominant disease, and those diseases you can't hide and then they pop up later because it's dominant. Okay? Whereas this girl had it, she married a boy that didn't have it, and how many children did they have? 4. And we would have predicted that 2 of them would have it and 2 of them wouldn't, right? Because we know her husband doesn't have it because he doesn't display the disease. He's little h, and half the time she's going to give the big H that she got from her father, and half the time she's going to give the little h that she got from her mother. Okay, so on your notes, go to where it says Mendelian patterns of human disease. Autosomal patterns. We looked at a recessive, now we looked at a dominant. Autosomes are any chromosome other than the sex chromosome. Any chromosome other than the sex chromosome. Both males and females are affected with equal frequency. And in pedigrees, females are circles, males are squares. I already gave you all that. Okay, take a look at this one. Is this a dominant pedigree or a recessive trait? Dominant or recessive? Tell your bio buddy and support your claim. Use the letter A.
They could have it should be dominant. Because they could have a big S.
Okay, I heard some people say this is a recessive trait. Is it? No, because if it were a recessive trait and you got it, then all they would have to give is what? Little a's, and their child would have got it. Right? But if it is a dominant trait, if this is how you inherit it, we're trying to figure it out. How's this trait inherited? If it was a dominant trait, what could these two genotypes be? Big A, little a, big A, little a, and they both gave, what were the odds that they were going to have a child that didn't have this disease? 25%, 1/4. Okay? So when you look at diseases like this is an autosomal recessive disorder. Okay? That's why it can skip generations. Now, this is another reason why you shouldn't marry your relatives. Because the diseases that you have packed away in your family that are recessive can end up displaying themselves because you're both hiding those recessive traits that could show up. Because see, that's what happened right here. Okay, cousins got married. And it increases the odds. Where did we see that historically? Royalty. Because royals married other royals, so there was inbreeding and there was a spread of what disease? Hemophilia. Right? Okay, so on your autosomal recessive disorders, most affected children have unaffected parents. Number 2, heterozygotes have an unaffected phenotype. Whereas if you look at this one, this is a dominant disorder. Affected children will usually have an affected parent. Affected children will usually have an affected parent. And number 2, heterozygotes are affected. And number 3, 2 affected parents can produce an unaffected child. Okay, and then I gave you for autosomal recessive disorders, I gave you some examples for you to know. Tyss disease, this is in our community. These are inherited of Jews of European or Eastern European descent. If you look right here, it's characterized by progressive mental deterioration, blindness, paralysis, epileptic seizures, and death, usually between ages 2 and 5. When the child is first born, there's no problem. But they're missing an enzyme, and as a result of that, missing that enzyme, then they deteriorate. Ironically, the reason why it's so prevalent in Jews of European descent is because if you were a heterozygote for that trait and in a concentration camp, you were more likely to be resistant of the pathogens in the concentration camp. So it kept that number high. Do you see? Okay, so we're going to talk about pleiotrophy when a trait expresses itself in different ways. The same thing for sickle cell disease. Sickle cell disease is more frequently found in countries or people who are black. And the reason is if you're a carrier for sickle cell disease, and so you see this higher in Africa, if you are a carrier for sickle cell disease, you are more resistant to malaria. So it keeps that gene at a higher frequency than what you would expect because it protects you if you're a carrier for it. Okay, so there's some different things like that. So we've already talked about some of these other ones. Autosomal cystic fibrosis, that's Tyss. We talked about cystic fibrosis when we talked about membranes. There is sickle cell disease, some dominant disorders, Huntington's disease. The bummer about Huntington's disease is it comes on when you're an adult, like in your 40s and 50s, and sometimes you've already had your kids by then, so you didn't know that you could possibly pass it along, and you lose control of your body. Another one, neurofibromatosis. These sometimes are called birthmarks, where you see a colored spot, and sometimes people have it on their face and they have it removed later. That is an autosomal dominant disease. If you see somebody who has a spot like that on them, one of the 2 parents had it because it's an autosomal dominant disease. But it could be back here. If it's left untreated, they can become tumors. And this would be an extreme case of that. Okay? This is another one. Achondroplasia is the most common form of dwarfism. and that is an autosomal dominant disease. And two people who are carriers for that, okay, that are carriers for the non-dwarfism, 1 in 4 of their children could be regular sized, even though they're two dwarf parents. Okay, so there's a bunch of practice problems that you can do in there, and then we'll pick up at 11.4 Beyond Mendelian Inheritance next time, and we will transition into our quiz.